quasi-crystal diffraction with an irrational metric and natural harmony. It's not a crystal, so how does it diffract? When the aluminium alloy melt is rapidly quenched, it produces several phases. The second phase is crystalline. And to Bayes Bragg's law, n lambda equals 2d sine theta. Here's n, 0, 1, 2, 3, 4, 5, 6. In this case, odd orders are suppressed by structure factors. But notice that n is integral, periodic, harmonic. That's Bragg diffraction. What about the quasi-crystal? N equals 0, 1, tau, tau squared, tau cubed, tau to the fourth. Tau is an irrational number. It's aperiodic and anharmonic. So how on earth does it diffract? In Bragg diffraction and crystals, the atoms exist on planes. The planes are separated by interplanar spacing d, which is unique and periodic in the crystal. Notice the red rays. The difference in path length is equal to lambda. That's the first order. And in second order, the difference in path length is 2 lambda. That's Bragg diffraction. In the quasi-crystal, it's different. There are multiple interplanar spacings, as we're going to see. In crystallography, if the multiple spacings are jumbled, that should produce diffuse diffraction, not sharp diffraction as we observe. So if we want to know how the phases add, we have to calculate the structure factor. The structure factor is independent of the scattering angle. But when we've calculated, we can come back and calculate the scattering angle. So that's the quasi-crystal. So that you don't get lost, here is a map of where we're going. Indexation, the quasi-structure factor and metric, analysis and irrational residue, the Quasi-Bloch wave digitized, and the diffraction measured, analyzed, verified, and complete. Here's the unit cell, manganese at the center, small atom, strong scattering factor. It's edge sharing, so the stoichiometry is aluminium 6 manganese. And notice this feature of the structure, normal to the 5-fold axis of 5 atoms in a circle on 2 planes. We're going to see those again. And the importance of the structure is that it's extremely dense. So dense that this is the structural driving force for the structure. I can say that for many reasons I give you 2. It is the truth that in all diatomic quasi-crystals, the ratio of the solute diameter to the solvent diameter has the same number. And why is that? Take the case of the second phase that I just showed you. It's face-centered cubic, which is already dense, and the small atom rattles inside a cage of aluminum atoms. But when it condenses to the icosahedral phase, the rattle space is squeezed out and the density increases by 17%. And this is energetically favorable for the icosahedral phase. Let's move on to the cluster. The unit edge width of the unit icosahedral unit cell stretches to tau squared in the hierarchic cluster. And in the hierarchic supercluster, tau to the power 4. Here it is, tau to the power 4. And here's manganese, here's the unit cell, here's the cluster made up of 5 unit cells on 2 planes, and the supercluster is 5 clusters on 1 plane in the section of the supercluster. The structure is infinitely extensive, periodically repeating with period tau squared. Here are the interplanar spacings, and every atom in this micrograph is measured, analyzed, and specified. We know the structure, so we can calculate the diffraction. And how do we do that? We know it doesn't obey Bragg's law. We have to calculate structure factors and then come back and calculate the scattering angle. First, we have to correct the indexation. Here's this diagram of the principal axis of the icosahedral structure. And normal to the principal axis are the diffraction planes. They're all 3-dimensional, geometric, simple and complete. Dimensions should not be multiplied without necessity. Mathematicians are dreamers. And how do we calculate the structure factor? First look at the black type for the crystal. We take each atom in a unit cell, project it onto a selected plane normal, sum the cosine phasors to find the amplitude for a selected Bragg beam. In the quasi-crystal, look at the blue type. We make two adjustments. First of all, because we have multiple interplanar spacings, we include a coherence factor, CS. We'll come back to that. Secondly, because our unit cell is not periodically repeating, we have to sum over the whole quasi-crystal, not just the unit cell. And to do this, we need an iterative procedure. The QSF for supercluster order P is equal to QSF order P minus 1 multiplied by this function, which describes the change of phase due to the stretching factor. And what is the result? There is no Bragg diffraction. If there were Bragg diffraction, it would occur on the ordinate axis where CS equals 1. But when we scan CS numerically, we find the quasi-Bragg condition occurs where CS has the value 0.894. It's the same on these beams that we counted earlier. It's the same for all the beams in Shipman's data. It's a universal number. So what is it? Notice that CS has the same role as the lattice parameter in the unit cell and has the same function as the reciprocal lattice parameter in the reciprocal cell on a plane normal. So it's one of those two, but actually CS is a consequence of the diffractive QSF. So it occurs on the reciprocal lattice. And we can analyze it. The index tau to the power m is equal to this Fibonacci sequence. And let me illustrate. Here it is, 1 tau, 1 plus tau, 1 plus 2 tau, 2 plus 3 tau, 3 plus 5 tau. And this term, 3 plus 5 tau, is equal to tau to the power 5, and the same with the other terms. This is the geometric series. And notice especially that this series is the sum of two Fibonacci sequences, one natural, one irrational. And we can rationalize this, or approximately rationalize this, by substituting for tau the rational number 3/2, which is 11% different from tau. And so we can separate into an rational part, a natural part, and an irrational residue, the subtraction of this from that. Here it is, remembering that CS is a factor. And it has a extraordinary feature when it's normalized against this number, that it's equal, exactly equal to the inverse of the metric. CS is a breathing strain on the reciprocal lattice. I can illustrate with the Quasi-Bloch wave. What is a Bloch wave? It's the lattice image in the two-beam condition. Look at the blue one. This is pseudo-Bragg-Bloch wave, commensurate on the unit cell, but not at higher orders. But when the blue wave is stretched by the metric function, it becomes a red wave, which is coherent at all intercepts, both long range and short range. This is exactly what we need to produce diffraction. Notice a further feature. Count the number of cycles. 1, 2, 3, 4, 5. And notice 1, 2, 3, 5, 8, 13, 21, 35. That's the Fibonacci divisor that we saw in the metric function. So we understand CS rather well. But what do we make of Shipman's claim? Long-range order with no translational symmetry. Is there long-range order? Yes, of course. That's evident in the diffraction. And is there no translational symmetry? No. Hierarchic Bloch waves are invariant under translations a tau to the power m, as you can see. We can summarize. The irrational part of the index stretches and digitizes. The natural part of the index commensurates and harmonizes. These solve the structure and diffraction for hierarchic icosahedra, analyzed, measured, verified by the quasi-lattice parameter and complete. So what about the measurement? This is my final point. Here's the Bragg law, here's the quasi-Bragg law, and this is how you measure the scattering angle. In the early days, several of us measured the lattice parameter and found a value 0.205 nanometers, assuming the Bragg law, because we had nothing better. But now we do know better. We correct with the index and the metric, and we find a value 0.29 nanometers. And why is that significant? 0.29 is the same as the diameter of the aluminum, which is equal to the diameter of the units, the edge width of the unit cell, which is the lattice parameter, measured, analyzed, verified, and complete. No suggested structural model can be complete without this diffraction analysis and measurement.